Good day and welcome back for our final installment on Lagrange multipliers. And in this video we are once again going to practice just one more additional example. And that example involves finding the absolute maximum and minimum values, i.e. extreme values, of a function of three variables subject to inputs lying on a sphere of radius 1 centered at the origin. And note, this is telling us that g of x, y, z is equal to x squared plus y squared plus z squared, our constraint equation. And note, this is the ideal scenario for us to apply Lagrange multipliers. And the Lagrange multiplier equations can immediately be written down as gradient f equals lambda gradient g, along with our constraint. And it is worth noting that after working a few of these examples, these initial steps should start to feel as though you're doing the same thing over and over again. In terms of the gradients, we have three equations, one corresponding to each of those partial derivatives. So I'm going to write out this intermediate step. F sub x is lambda g sub x, f sub y is lambda g sub y, f sub z is lambda g sub z, and then we have our constraint. And if we go ahead and put this specifically in terms of our functions f and g. So we have the partial f sub x, 2x y squared z squared, equals lambda times 2x. And then we have 2x squared y z squared is lambda 2y. And then partials with respect to z, 2x squared y squared z is equal to lambda 2z. And our constraint, x squared plus y squared plus z squared, is 1. And to attack this problem, we are going to take an approach similar to one of our previous examples. It's difficult to maybe work with a single equation at a time, but what we are going to instead focus on is the lambda, which appears in each of these three equations. So note, in the first equation, lambda is equal to y squared z squared. In the second equation, the two y's cancel, and it's x squared z squared. And in the third equation, the two z's cancel, and we have x squared y squared. And note, if you were paying particular attention in our previous video when we were talking about dividing by lambda, you might be worried about a particular occurrence. Is it possible for x, y, or z to be 0? So let me just note, if x is equal to 0, just for fun, then in the first equation you would have 0 equals 0, and you're good to go. In the second equation, if x is 0, the left-hand side is 0, which forces either lambda to be 0 or y to be 0. Similarly, in the third equation, it forces lambda to be 0 or z to be 0. So if lambda is not 0, which is going to correspond to the work that we have done to the right, then x equals 0 is going to force y and z to both be 0. But note, this is not possible in terms of our constraint equation, because x squared plus y squared plus z squared is 1. And even though we don't have to worry about x, y, and z being 0, if 1 is 0, they're all 0, and that's not possible, a real possibility that we need to consider and we'll have to revisit in a few moments is, can lambda be equal to 0? So let's just put that to the side and we'll come back to it. Let's continue with our observation to the right. These first two equations, since we've mentioned x, y, and z are not 0, we can divide by z squared and write y squared is x squared. Similarly, for the right two equations, since we're assuming x is not 0, we can divide by x squared and write z squared is equal to y squared. And let's think about how we can now substitute this information into our constraint. We could replace the z squared with y squared, and we can replace the x squared similarly with y squared. So our constraint equation is going to become y squared plus y squared plus y squared equals 1, 3y squared equals 1, or y squared is equal to 1/3. And because x squared equals y squared equals z squared, which now we've said is 1/3, that implies that all x, y, and z would be plus or minus the square root of 1/3. Now I would like you to think about this for a moment. If x, y, and z can all be plus or minus the square root of 1/3, how many points do we have where those extreme values can occur? And the answer is quite a few, probably more than we want. But if we think about a generic form, we have two possibilities we can plug into each of these three coordinates. So if I can put 2, 2, and 2, we multiply those three together, so there's 8 possible choices. So it's the multiplicative principle of counting. And those 8 choices are essentially the same, plus or minus square root 1/3, plus or minus the square root 1/3, plus or minus the square root of 1/3. And remember how our function f was defined. And since I'm low enough on the page, I'm just going to write it below. F is the function x squared, y squared, z squared. So it does not matter which of the plus minuses you're getting. Each and every one of these 8 possibilities is going to have exactly the same output. You will have 1/3 times 1/3 times 1/3, because plus or minus the square root of 1/3 squared is 1/3, which is 1/27. Now, we are unsure at this point whether that's going to be a maximum or a minimum, but before checking some other points, let's go ahead back to this lambda equals 0 that we had left hanging earlier. And note, if lambda equals 0, our 3 gradient equations can be significantly simplified. They would become 2x y squared z squared is 0, 2x squared y z squared is 0, and 2x squared y squared z is equal to 0, and then we still have our constraint. And what I would like us to think about is how can these first 3 equations be satisfied while still satisfying the constraint. So if just one of the variables is 0, that is okay. So if x is equal to 0, all 3 of these equations work. If 2 of the variables are 0, so x and y are both 0, y and z are both 0, x and z are both 0, that's perfectly fine. But note, not all 3 of them can be 0, as we already observed above, because then they would not solve that constraint equation. So this gives us a whole bunch of other possible points, and I'm not going to try to list them all once again, but instead let's just describe them. So this could be satisfied by points of the form a, b, and c, with 1 or 2 of a, b, and c being 0. And I don't have to be any more specific. There's a whole bunch of possibilities, but note, regardless of any of those possibilities, if a, b, or c is 0, what is our associated function value? It's also 0. So note, this 0 would correspond to the absolute minimum, and it can be achieved at a whole bunch of different points. And the 1/27th we encountered previously would be where the maximum value is achieved. And I do want to note that this is most definitely an involved example, probably the most involved example we've encountered in terms of different possibilities and subtleties involved. But if you can really follow through and understand the thought process involved with this problem, you will certainly be prepared for what you will see on a homework assignment or an exam. I think this would be more difficult than we would encounter in those scenarios. So make sure you're working practice problems. If you have questions, drop me an email or stop by. So stay tuned and take care.